Hello, everyone, and welcome. Today, we're going to dive into a fascinating area at the intersection of education and artificial intelligence, knowledge tracing. Specifically, we'll be exploring a powerful technique called AKT, or attention-based knowledge tracing. Think of it as a way for a computer to understand what a student knows, just like a good teacher does. We'll start by breaking down the core idea of AKT, and then we'll look at some of its exciting variants like MAC, RACT, and MFA-DKT, which build upon this foundation to create even smarter models. By the end of this session, you'll have a clear understanding of how these attention-powered models are revolutionizing personalized learning. Great. Let's get started. Here's a roadmap of our journey today. First, we'll start with a simple analogy to understand the evolution of these models. Then, we'll break down the core concepts and key parameters that make AKT tick. To make it concrete, we'll walk through a live calculation demo. After that, we'll compare AKT with older methods to see exactly why it's a game changer. Finally, we'll discuss how you can integrate this powerful tool into your own research and wrap up with a summary of the key takeaways. So, let's begin with a fun analogy. Let's think about how different models work by using a simple analogy. Imagine your brain is a library of knowledge. Traditional methods like DKT, they're like trying to remember everything with a compressed memory. It's efficient, but you lose a lot of detail. You know you read a book, but you can't quite recall the exact page or paragraph that was important. Then came improvements like DKT+. They started adding subway maps between different pieces of knowledge. This helped the model understand that knowing concept A is connected to understanding concept B. It's a step forward, but the map is still a bit static. Now enter AKT. Think of AKT as a smart reviewer with a highlighter. As you learn, it doesn't just store information, it actively highlights the most relevant parts of your past learning experience that are crucial for solving the current problem. It's dynamic, it's focused, and it's incredibly efficient at connecting the dots. This is the core power of the attention mechanism we'll be discussing. So, what makes up this smart reviewer? Let's break down its core concepts and key parameters. Core concepts. Exercise. This is the question or problem the student is trying to solve. Knowledge concept. This is the underlying skill or fact being tested by the exercise. Attention. This is the magic sauce. It's the model's way of deciding which past exercises and concepts are most relevant to the current one. Prediction. The final goal. To predict how likely the student is to answer the next question correctly. Key parameters. D. Dimension. Think of this as the richness of the description. A higher dimension means we can capture more nuanced details about each exercise and concept. Q. Query. This is the question the model asks about the current exercise. What do I need to know to solve this? K. These are the tags or keywords attached to all the previous exercises and concepts. Value. This is the actual content or knowledge associated with each of those past keys. In short, the model uses the query from the current problem to scan through all the keys of past experiences, finds the most relevant ones using attention, and then combines their values to make a smart prediction. Let's make this concrete with a simple example. Imagine a student has just answered 3 questions about algebra and geometry, and now they face a new question about Pythagoras. Step 1. The query. The model looks at the new Pythagoras question and creates a query vector. This vector represents what knowledge is needed to solve it. Step 2. The match. The model then compares this query vector with the key vectors of all the previous questions, like linear equations, angles, etc. It calculates a similarity score for each. The higher the score, the more relevant that past question is. Step 3. The weight. These similarity scores are then converted into attention weights. Think of this as the model saying, the question about right-angled triangles from earlier is 90% relevant, while the one about fractions is only 10% relevant. Step 4. The prediction. Finally, the model uses these weights to create a weighted sum of the value vectors, the actual knowledge states, from the past. This gives it a highly informed guess about the student's current understanding of Pythagoras, allowing it to predict the outcome with impressive accuracy. So, how does AKT stack up against the old ways? Let's draw a clear comparison. Memory versus attention. Traditional models rely on a fixed-size memory cell, which can get cluttered. AKT uses attention to dynamically focus on the most important past events, like a spotlight, making it much more efficient and precise. Static versus dynamic. Old methods often have a fixed way of connecting knowledge concepts. AKT's attention is dynamic. It changes with every new question, allowing it to adapt to the student's current task in real time. Black box versus interpretable. It's often hard to understand why a traditional model made a certain prediction. With AKT, the attention weights give us a clear window into the model's decision-making process, showing us exactly which past experiences it considered important. Single versus multiple relationships. Earlier models struggled to handle complex relationships between multiple knowledge concepts. AKT excels at this, as it can assign different attention weights to many different past concepts simultaneously. In essence, AKT is not just an incremental improvement, it's a fundamental shift in how we model student learning. The beauty of AKT is its flexibility and power, which opens up exciting new research directions. Let's see how it can integrate with two key areas. OCZ, Optimal Challenge Zone. We know students learn best when the material is neither too easy nor too hard. AKT's precise understanding of a student's knowledge state allows us to pinpoint their optimal challenge zone with great accuracy. We can then use this information to recommend the perfect next question, maximizing learning efficiency. Multimodal fusion. Learning isn't just about answering questions correctly. It's also about how long you take, how you interact with the interface, or even your facial expressions. AKT's framework is highly adaptable. We can feed all these different types of data, let's call them multimodal data, into the attention mechanism. The model can then learn to pay attention not just to what you answered, but how you answered it, leading to an even deeper understanding of the learning process. Let's quickly recap what we've covered. At its heart, AKT is all about applying the attention mechanism to knowledge tracing. This allows the model to focus on the most relevant parts of a student's learning history, leading to more accurate predictions and a clearer understanding of their knowledge state. We also touched upon the exciting ecosystem of variants that have grown from the original AKT idea. Make looks at different types of attention to model behaviors like forgetting. RACT uses reinforcement learning to not just predict, but to actively guide the student's learning path. MFA-DKT combines the best of both worlds, merging deep learning's power with attention's precision. This field is evolving rapidly, and AKT has proven to be a cornerstone technology driving this progress. That brings us to the end of the main presentation. I hope I've managed to shed some light on how AKT and its variants are changing the face of educational technology. Now, I'd love to hear from you. If you have any questions about the concepts, the applications, or anything else we've discussed, please feel free to ask. I'm here to help clarify. Thank you all very much for your time and attention today. It's been a pleasure sharing this topic with such an engaged audience. I hope you leave with a newfound appreciation for the power of attention in AI and its potential to transform learning. Have a wonderful rest of your day.